Hello everyone, welcome to my presentation. My name is Akaki Mamageshvili and I'm from ETH Zurich. So today I will talk about sequential solutions in machine scheduling games. This is a joint work together with Kong Chen, Paul Gisler, Mateusz Michalak and Paolo Pena. So first, let me give you the outline. So first I will talk about preliminaries and definitions. Then I will discuss lower bounds, and then I will discuss upper bounds for two machine scheduling games. So what is the problem we study in this paper? We have n unrelated machines and n jobs, where for each pair of machine and job, we have a runtime Tij. So I stands for machine index and J stands for job index. And Tij means that this machine needs, iMachine needs Tij time to complete J job. Jobs are owned by players, and every player cares to minimize its own cost and doesn't care about any other player's costs or what is the general solution or general overall load of machines. So cost of a job is the total completion time of the machine that this job is assigned to. So when machines get jobs assigned, machine finishes completion of jobs after the total time of completion of all jobs, and this is the cost of all jobs. So jobs are not run on the machine sequentially. So all jobs need to be finished to get the result of each job. So makespan is the maximum weight of all machines. And in this work, we consider sequential arriving of players of jobs. Of course, we assume that players are rational, and we have a full knowledge setup where everyone knows that everyone is rational, and they also know who arrives next. So there is a famous course of simultaneity that is described by Lemme et al. And it says that simultaneous games can have arbitrarily bad makespan compared to optimum makespan. So that's why the authors consider subgame perfect Nash equilibrium solutions, where the solution, so the final assignment, is obtained by sequentially arriving players. So when a player arrives in the game, it sees what the previous players did and what are the next players, what is the next player's arrival order. By opt, we denote social optimum. So this is the assignment which minimizes the makespan over all assignments. And we also denote this makespan itself with opt. So we consider three different solution concepts and three different measures of these solutions. So for fixed runtime matrix T, we first define sequential price of anarchy for this particular matrix T. And this is the worst order of players. And then we compare, so we consider the worst order of players, player arrivals, and we compare makespan of the subgame perfect equilibrium to optimal makespan. Then we consider sequential price of stability for this matrix T, and here we look at the best order of arrivals. So the last solution concept we consider is adaptive sequential price of stability. In this, we consider arbitrary arrivals. So this means that the sequence is not fixed in advance, but it changes depending on the decisions of the previous arrivals. And to calculate the sequential price of anarchy or sequential price of stability, for a general game, we consider the worst possible game T. So the worst possible means that we are maximizing this ratio of subgame perfect equilibrium make span over the optimum. So here are some examples. We'll look at the bad Nash equilibrium example, where the Nash equilibrium can be arbitrarily worse than the social optimum. So we have two jobs and two machines. On the first machine, the runtimes are epsilon and 1, and on the second machine, runtimes are 1 and epsilon. So one equilibrium of this game is that first job goes to second machine, so the runtime of this machine is 1, and second job goes to first machine, and runtime of this machine is 1. So this is equilibrium because no job wants to deviate. So if we consider, for example, first job, if it deviates, the cost becomes 1 plus epsilon instead of 1, and the same with the job 2. As you can see here, social optimum is epsilon, and it is obtained by job 1 going to machine 1 and job 2 going to machine 2. So we can see that if we take epsilon converting to 0, sequential solution gives optimum in this case. So the price of anarchy is unbounded. While if we consider the sequential arrival of players, then the first job would get assigned to first machine and second job would get assigned to the second machine, and this would give us the optimum. This is also a Nash equilibrium solution, but here we make a point that some Nash equilibria can be arbitrary bad. So in this example, we have sequential price of anarchy larger than 1. So we have 2 machines and 3 jobs, and the runtimes are 2e, 1 and 2 minus e on the first machine, and 2 minus e, 1 plus e, and 1 plus e on the second machine. So with dark, bold intervals, we denote the subgame perfect equilibrium solution, and the make span here is 3 minus e, while in the optimum the make span is 1 plus 2e. So this 3 denotes how the game unfolds. So in the root we have job 1, and 2 edges denote 2 options for this job. So first edge denotes first machine, and second edge denotes second machine, and so on. So the red state is the subgame perfect equilibrium, and green state is the optimum make span solution. And here we see that if we take e goes to 0, the subgame perfect sequential price of anarchy goes to 3. So as I already mentioned, this problem was introduced in 2012 in Lemme et al., and the paper was called The Curse of Simultaneity. And what they showed is that with sequential arrivals, so not simultaneous play, the ratio between the subgame perfect equilibrium make span and optimum make span is at least finite, so not infinite, which was later improved by Bilo et al., and they showed that subgame perfect sequential price of anarchy is upper bounded by 2 to the power n. So the original bound was 2 to the power n times m, so m is number of machines. And they also obtained the super polynomial lower bound of 2 to the power theta of square root of n, but here they use many machines. And for 2 machines, Hassim and Yovel in 2015 conjectured that subgame sequential price of anarchy is at most 3. And this example from the previous slide is actually from their paper. So we give counterexample to this conjecture by constructing an example. So these are the runtimes. We have 2 machines, but we need 5 jobs. And we see that if epsilon goes to 0, then optimum solution is actually 1. So max span is equal to 1, so converges to 1, while subgame perfect equilibrium is denoted by gray boxes, and it converges to 4. So this was a counterexample, and then we showed actually that subgame sequential price of anarchy grows linearly with n. And this example we found by computer simulation, but it was not straightforward because for enumerating all possible decision trees and the decision made by players, we would have to check 2 to the power 2 to the power n possible states, and for each of them we need to solve linear programs, and this was too slow even for n is equal to 5. But by a lot of symmetry breaking and some structural properties, how decision trees look like in the sequential games, we reduced this number considerably, and we were able to find these loads that give higher sequential price of anarchy. So the proof sketch of the theorem. So the runtimes look like this. We take a number of jobs equal to 3k plus 2, and we have 2 machines. And these are the running times. So this pattern k plus 1, 0, 0 on the first machine and 0k repeats itself until the last point where we have a job indexed 3k minus 2 and job indexed 3k minus 1 having slightly different loads. So here we don't have epsilons because we allow that we can break the ties in a suitable way for us in the construction. So as you can see, optimum here is equal to 1 because all jobs up to 3k minus 2 can be scheduled to machine with runtime 0, and then the last 2 jobs we assign to machine 1 and 2 respectively. While in the sequential solution, we have a make span k plus 3 on the second machine and k plus 1 on the first machine. So it grows linearly. So apart from this conjecture, we also obtained some upper bounds. So first, we considered sequential price of stability and showed that with n jobs, sequential price of stability cannot be larger than n half plus 1. And the proof sketch is that first we take the optimum assignment, and then the jobs that go on the first machine, we let them go first, and then the others follow. And on the induction, by the induction on the number of players on the first machine, we can show that sequential price of stability cannot be larger than this number. And we remark that this proof mechanism does not generalize for 3 machines. So for 3 machines, different logic is needed. So we also looked at this adaptive permutation. So on each path from the root to the leaf, we have some permutation, but this permutation is not globally fixed. And this allows us to punish players if they make some unfavorable decisions. And for 2 machines, we show the theorem that there is some adaptive order which achieves the optimum make span as a sequential solution. So here, proof is by backwards induction. So we get some constrained optimum. So we know what is the constrained optimum in each subtree. And the key property is that there is always some player who gets worse outcome if this player deviates, and we will put this player next to implement the optimum solution. But this adaptive order doesn't help to reach optimum answer for already 3 machines, and this is example with 3 machines and 3 jobs. So these are runtimes, as you see in this matrix. So as you can see, optimum is 4. So we assign job 1 on machine 2 and job 2 and 3 are on machine 1. Now consider any order of arrivals of jobs. So suppose the first to move is job 1, then it is clear that it will choose first machine because nobody will join and he will enjoy 4 minus epsilon cost. Then second player will choose M2 because he knows that, or third player because he knows that the last one will choose the machine 3. So now if we assume that the first job to move is job 2 or job 3, so they are symmetric, so it doesn't matter which one we consider, then we see that it will choose machine 2 and enjoy price 3. So in the first case, given that first job is on the first machine, the cheapest solution costs 6 minus epsilon, and in the second case, we see that the best solution again costs 6 minus epsilon. So if we take epsilon cost goes to 0, we get that adaptive sequential price of stability goes to 3/2. So to the end, we also show that sequential price of anarchy is actually also bounded linearly. We show that for 2 machines, the sequential price of anarchy is at most 2 times n-1. And the proof sketch is following. We bound the difference in the make span by adding just 1 job. And then we used induction on the number of jobs. So that was it. Thank you. And if you have any questions, please ask.